Okay, Drake fans, I'm back on the TR4. No transmit on 10 meters. I thought there, there just shouldn't be that much wrong with this load capacitor. Yes, it did read open. Yes, I fixed the solder joints. Yes, it appears to work. But if that final amplifier is in that bad a shape, it shouldn't work on 15, and it does. So I did signal tracing back towards the local oscillator, back to the cathode follower. Okay, signal levels, roughly a couple of volts peak to peak, back to the cathode follower until 10 meters, and the signal level drops off. Well, that suggests something before that, and what's before that's basically the VFO and the local crystal oscillator. What's easy to miss in, for example, in communications receiver theory, you see the oscillators, the mixers, the amplifiers, the detector, all that jazz. It's easy to see that oscillators have frequency. On 10 meters, there's a VFO, about 5 megahertz. There's a carrier oscillator, crystal based, 9 megahertz, and then the difference is made up by the local oscillator at 43.0 megahertz. That's pretty low frequency. These tubes in this radio, the final tubes are good for 110 megahertz. These small receive tubes should be good in the UHF region. There's no reason for significant roll off at 30 megahertz. But it's easy to overlook the fact that the signal we hear out of the speaker is not because of the strength of the signal in the antenna jack. That should be obvious. That's microvolts versus volts. But what that tone you're hearing is made of is not just a signal from that generator. Yes, that's the frequency. It's dividing down to an audio frequency. But what's important here is not only the frequency of the oscillators, but the signal strength. Because literally, the strength of that S meter reading is dependent on the signal strength from each of those oscillators. And if any of them are off, low output, that signal level will drop proportional to how much the oscillator signal has dropped. Yes, mixers mix frequency, but they also require certain amplitudes. But we can't have one signal at 10 volts and one at half a volt. That ain't going to work. We might expect the output will be more like a half volt. It'll be very low. So I suspect the local oscillator crystal at 43 megahertz for 10 meters, I can't prove it. There's lots of bad information online about taking crystals out to test them. That's like the similarly bad advice to take tubes out to test them. In the Tektronix manual for the old RM35 scope series, don't take tubes out to the tube tester. Putting the tubes in the circuit is the best place to test them. All it takes is a little bit of basic knowledge and a voltmeter to know if the tube's working correctly. Measure the cathode resistor. That'll tell you everything you need to know for general operation, for DC bias anyway. But crystals are dependent on their frequency. They should oscillate at their rated frequency. But the drive level is critical. And in this rig, like other crystal oscillators, it's not an amplifier and a crystal, it's an amplifier and LC circuit that's resonant and the crystal. And the LC circuit is required to start the crystal, because a further parameter of a crystal is it must start on the intended resonance for the intended frequency, and crystals can have 3 or 4 resonances. You don't want it starting up in the wrong mode. So the LC circuit kickstarts a crystal on its intended frequency and helps it stay there. That lends to stability. If the crystal is off frequency, its output, so to speak, will probably be low, and it won't be oscillating at the frequency that is optimum for the LC circuit of the oscillator. Critical point. And you won't find this in basic electronics. This is advanced stuff. So to evaluate this, where I cannot measure the crystal oscillator for the local, because even getting a finger near it changes the frequency, it's very touchy, I'm using the approach of testing the entire receiver, beginning with 80, 40, 20, 15, and 10. With a 1 millivolt RF signal in from the generator and through an attenuator in the antenna jack, I align it on 80 meters for about an S9 reading on the meter. If I get down here and look straight in, it's S9. Just a convenient landmark. I land on 40. The level's just a tiny bit different. Well, with 40 meters, there's another oscillator in the circuit in the premixer, and that's a crystal oscillator. On 20, the signal's just a shade different, but not greatly. On 15, S9 may be a bit more. On 10, on 10.2, 28.3 megahertz, the signal falls way down. First off, I couldn't find a signal. The VFO dial is on the 28.5 band segment plus 300 kc, 28.5. I put the generator on 28.5, nothing. It's not completely dead. Why is there no signal? Well, I'll show you what happened. I switch 28.5, frequency 28.8 megahertz. Nothing. No signal. Where'd it go? Whoops. Uh-oh. There it is. It's supposed to be here. Why is it there? And what's up with the S meter being an S unit low? Do we really care about one S unit relative on a receiver on a span from 80 to 10 meters? No, not really. This radio has plenty of sensitivity. Why do I care about one S unit? It's trivial. But this is the information necessary to absolutely prove beyond a doubt that not only is the 10 meter LO crystal defective, but that is the cause of why it will not transmit on 10 meters beyond about a few tens of watts. And these observations on receive correlate exactly with what I saw on the bird watt meter and transmit, and I'll explain how that is. The first observation is there's no signal on 28.8. It's 1, 2, 3, 4, 5, 4.5 kc off frequency. That's how far that crystal has shifted. That crystal is junk because it's not oscillating at at 43, I think it is. It's oscillating at 43.005. Handy dandy little picture in the context of my poor videos. Receiver chain, top left RF amplifier antenna, lower VFO and local oscillator mixing. Those two mix together to make a frequency. They mix in the mixer with a 9 megahertz carrier oscillator. Through detector makes a speaker audio. The frequency of all these oscillators, the LOs and the VFO and the carrier, determine the receiver frequency. So if any of them are off, the receive frequency will be off. And there's a rough illustration of the 5 megahertz VFO, 43 megahertz local oscillator, and 9 megahertz carrier. They're all the same amplitude. The output's happy. But when the crystal at 43 megahertz is very, very low amplitude, the result is a very low amplitude output. And if that crystal is parallel resonant and the asymptote's at 43, and that crystal is now off by 5 kc, which is a lot, you can figure, I don't know, a good crystal is a couple to 10 parts per million. But this is off too much. 5 kc is too much. The TR3 filter crystals, sideband filter crystals, were off a couple of K and it was junk. So that goes away from where the ideal response is. If that's a parallel resonant response for the LC network in the oscillator, it's shifted way off to the capacitive side. So the oscillator will be weak. That's a bunch of drift. But this right here is probably enough to prove the crystal's no good, but that doesn't speak to the amplitude. What do I care if it's 4 kc off on a mechanical dial? Well, I can always correct that. And it's probably off a bit because I aligned the LO to peak. Now I can adjust the inductor in the LO circuit to bring that frequency down, but then it won't have peak output, so I'm shooting myself in the foot. But noting that the convention for S meters is about 5 dB per S unit, that means that the local oscillator signal is weak by a good 4 dB, maybe 5 dB. And lo and behold, that amount, if you take 5 dB off 125 watts transmit power, what do you get? Well, if 3 dB is halving it, that's about 60 watts. Well, let's say an S unit is twice that. Let's say 2 3 dB losses. 2 3 dB losses, and it's about an S unit low. So let's assume 6 dB just for giggles. Pick whatever figure you want. Hear it running? Something ain't happy. But take 3 dB off of 125, you get about half, which is about 60. Take half that, you get 30. And that is about how much power this rig was making on 10 meters in transmit. So, proof. And this is beyond ordinary radio theory. This takes really knowing all these circuits and systems up close. But that is the process for checking out these local oscillator crystals where we don't have a way to do it with an external circuit. And it's risky to test crystals externally because if it's not the same circuit and the same drive level, the crystal's response will be different. So it really needs to be tested in the circuit in the rig. And there's how to do it, similar to testing the sideband filter by the S-meter response. So that's why the TR4 won't transmit on 10. And without proper drive, there's no chance of adjusting correctly the pi network and the neutralization. So what I did is I found an injection point through a decoupling capacitor to drop in channel 2 of the RF waveform generator. I pulled the crystal out of the oscillator and jumped in the generator, and I can set up to about 3 volt peak to peak. I can set the oscillator level. So then I can inject a LO signal, and that should give the correct S meter reading, and that should give the correct drive. There should be about 140 volts peak to peak on the final grids, but then that should allow me to go on and properly get power from the final so I can set the pi network and neutralize it. So there's some advanced radio theory from K8BYP. And an important footnote, there's the signal level from the generator, 28.8 megahertz. That level results in an S meter reading that's 1 S unit low, almost precisely. To get the S meter to read S9, it's necessary to make this 4 millivolts peak to peak. So that's a 4 times, let's say exactly, a 4 times increase in signal strength from the generator to increase the S meter from S8 to S9. So question to you, is that 4 times increased? Does that correlate with 6 dB? You look up the dB tables. You'll find that's a real good correlation, although it's not very accurate. It's only single digit, but there is a correlation there. So that's basically a total proof that crystal is bad and it's a cause of the transmit problem. And you wouldn't think so by seeing the S meter off just a hair. You wouldn't expect that huge of a decrease in transmit power, but realize the transmitter has no AGC like the receiver. The receive AGC tries to keep the signals reasonably level, but the transmitter AGC only works to fold back the final amplifier if it sees excess drive. So in normal conditions, the transmitter has no AGC, so there's nothing to keep it level.